Hi students, welcome to another video of PYQ discussion, and today we are going to discuss questions from moving charges and magnetism, 12th physics. Okay, see, as we know, this question in this particular chapter is based on magnetic effect of moving charges. If you analyze the past papers, like previous papers, especially the last 2 years paper, you can see on an average of 6 to 7 marks questions are coming from this particular chapter on an average of 6 to 7. If you cross check all the sets of last 2 years, we can see that many marks, like 7 marks or average of 6 marks from this one single chapter itself. Okay, right. So the major concepts in the chapter, we know different sources of magnetic field. That is the key concept. This chapter and the next chapter followed by this, we have magnetism and matter. In these two chapters, we discussed different sources of magnetic field. And in this chapter, we focused only on moving charges or current carrying conductors, magnetic field produced by them. Right? And in the next chapter, magnetism and matter, we considered another source of magnetic field, which is called bar magnet. So in this discussion, it will be based on basically the moving charges and the current carrying conductors. The major topics we discussed in the chapter is Biot-Savart law and its applications, Ampere circuit law, its applications, right? Then magnetic Lorentz force acting on a moving charge, magnetic force acting on a current carrying conductor. See, current carrying conductor is a source of magnetic field because there are moving charges there, right? Yes. And then followed by that, current carrying loop of wire can be considered as a magnetic dipole. Then force or torque acting on that particular dipole or the loop of wire. And as an application of that, we had a moving coil galvanometer also in this chapter. So these many topics we have to cover, like from the chapter. And when we go through the questions, we'll get an idea about from which part, from which topic we get what kind of questions and all. Okay. So let us move on to the questions. Question number 1. A loop of carrying a current I in clockwise direction, S, is placed in XY plane in a uniform magnetic field directed along Z axis. The tendency of the loop will be 2. See, a current carrying loop of wire is kept in a uniform magnetic field along Z axis. Okay, so if you consider see, this is X axis and this is Y axis, and if you go for a current carrying loop which is kept in this XY plane, see, as per the question, that loop of wire is kept in XY plane, then the magnetic field is actually acting out of, like along the negative, Z axis. That's what the direction of magnetic field given. So magnetic field is acting along Z axis. What happened to this loop of wire is the question. So option says it moves along X axis, it moves along Y axis, it will shrink, that is contract, or it may expand. Okay, so we have a clockwise current also given. So we mark the current in the loop as clockwise. We know force acting on a current carrying conductor. If you consider a small portion of this particular loop of wire, see, this is the small element, line element, current carrying element, and the current is going towards right? So it is clockwise current. So current is flowing towards right. Magnetic field is out. See, magnetic field is out. The index finger along direction of magnetic field. Fleming's left hand rule we are going to apply. Yes, magnetic field is along the Z axis. Direction of current is towards my left. Okay, and then what about the direction of the force acting on that particular element? The force acting on that particular line element will be just in the downward direction. If you consider a diametrically opposite line element, suppose a DL, if I'm going to consider here, the only difference there, current is in the opposite direction, right? Current is in the opposite direction. So what about the force? Force will be just reversed. Okay, so if you check, apply the left hand rule, Fleming's left hand rule, you can see force acting at different points, at different line elements on this loop will try to contract it, because of the direction of the force. Look at the force. Force everywhere is acting towards the center of the loop, right? Yes. So we can say the direction of the force is acting towards the center, which will try to contract the loop. So option C, that loop will shrink. That is the answer. Okay. Right. Now let us move on to the next question. A 10 centimeter long wire lies along Y axis. It carries a current of 10 ampere in positive Y direction. Okay, a magnetic field B is given in the vector form 5 millitesla. Okay, remember millitesla J cap minus 8 millitesla K cap exist in the region. Okay, the force on the wire is, we know the equation for force acting on a current carrying wire, F is equal to B into I L into L into sine theta. Right, look at that. Magnetic field is given in the vector form, right, and the length is the other vector in this like given expression. So in vector form, this equation can be I into L cross B, right? That is what the equation we know. In the vector form, the same equation can be represented like this, I into L cross B. Yes, so now let us find what is this L and B cross product of the two is to be calculated. What is current given? Current in the question is given as 1 ampere. 1 ampere current. Current is a scalar quantity, we know. Yes, so current to be multiplied finally after finding L cross B. But nothing to do after because current is 1 only. So that calculation is easy. Now, L cross B. What is L? Magnitude of L and its direction. Look at this. Length of the wire is given as 10 centimeters. If length is 10 centimeter, it is direction of length of the wire is always along the direction of the current. So if you want to write this as a vector form, like length as a vector, you should check what is direction of current given. Look at the question, 1 ampere current in the positive y direction. So L is actually 10 centimeter J cap, right? Because current is along positive y-axis. Direction of length, is going to be along the direction of current. So that is in centimeter. This is in millitesla. Magnetic field is in millitesla. So we take care of all those conversions. Right. So now we can just go for L cross B. That will be the force acting on it. Okay, because current is, I told you, current is 1 ampere. So nothing to be multiplied with. So how will you find L cross B? We know I cap, J cap and K cap. We can go for the determinant operator here. So I cap first one is going to be L. L has only J component, right? So I is 0. J component is going to be 10 into 10 raised to minus 2. That is 10 centimeters converted to meters. No K component, so it is 0. Okay, what about B? B is going to be 5 millitesla. Check the unit vectors J and K. So I is 0 actually, nothing from along x-axis for B magnetic field. And what about J cap? It is going to be 5 millitesla, so 5 into 10 raised to minus 3 along J cap, and minus 8 millitesla, so 8 into 10 raised to minus 3 with a minus sign for K cap. So now we know when we go for, this is the force, right? Force which is equal to L cross B. This is how we calculate it. Now L cross B. Just go for L cross B. What is the result? Nothing to do with, I cap. I cap we are going for minus 10 into 10 raised to minus 2 is going to be 10 raised to minus 1. So 10 raised to minus 1 into minus 8 into 10 raised to minus 3. Correct? Because we multiply these two and we subtract this. Minus what? 0. So I cap what is done? I cap. Now what about J cap? When you go for J cap, 0 minus 0, right? Nothing more. When you go for K cap, again 0 minus 0. So only I cap exists in our calculation. So check it, this value F is equal to I into L cross B. That is what the result we are looking for. So I is 1 ampere. So 1 ampere into 10 raised to minus 1 into 8 is going to be minus 0.8 into 10 raised to minus 3, right? And minus 0, so nothing more. So this is what we are getting finally, minus 0.8 into 10 raised to minus 3 Newton. And 10 raised to minus 3 Newton can be millinewton. So we get minus 8 millinewton along I cap. See, that was along I cap. Yes. So that is option B. Fine. So let's move on to the next question. Question number 3. A galvanometer of resistance G ohm is converted into an ammeter of range 0 to 1 ampere. I ampere. Right. If the current is through the galvanometer is 0.1% of I ampere, the resistance of the ammeter is. See, read the question once again if you're confused. You're asked to find out what is the resistance of the whole ammeter. Okay. Resistance of ammeter. You are not asked to calculate what is the shunt resistance to convert. No, you're asked to calculate what is the total resistance of the ammeter. What is actually the ammeter all about? A galvanometer can be converted to an ammeter by connecting a shunt in parallel, right? A shunt in parallel. This is S. So that whole device now is called an ammeter. See, this is an ammeter. So this ammeter will have some resistance. How will you calculate the resistance of that ammeter? Resistance of the ammeter is the equivalent resistance of the parallel combination of galvanometer and the shunt together. Okay, so we have to find out what is the shunt resistance to be connected. That and galvanometer resistance. Galvanometer resistance is given as G ohm. Okay, so that value is G only. Right, so we have to find out S in terms of G. Then we will find out the resultant of the two. That is our final answer. I hope the question is clear now at least. Yes, and we know the conversion of galvanometer into ammeter. We have Ig into G is equal to I minus Ig into S, right? This is how we did it. All right, so we have to find out S in terms of Ig, right? So shunt in terms of G, galvanometer resistance. Now, what is the relation between I and Ig given here? It says current through the galvanometer, which is Ig, is equal to 0.1% of the range of ammeter. This I is the range of ammeter. Ig is what we're looking for, right? So given that Ig is equal to 0.1 by 100 times I, 0.1% of the total current, right, is going to be the galvanometer current, Ig. So that value we are going to substitute here. Then we get value of S. Finally, 1 by S plus 1 by G will be 1 by R equivalent. Then you can find out the total resistance. So let us find out, here it is Ig into G is equal to, see what is S finally? We have to find S directly from that. S is equal to Ig into capital G divided by I minus Ig. Correct. So this is going to be Ig. What is Ig? 0.1 by 100. So 0.1 by 100 times I divided by I minus Ig. I minus 0.1 by 100 into I. The whole multiplied with G. Yes, so simplify this. So we will get 0.1 by 100. I gets cancelled. How will you simplify this? 100 minus 0.1. So we get 99.1 divided by 100. Correct? So what is this finally? See, into G. Yes, into G. 100 and 100 gets cancelled. We get 0.1 G. So we get shunt resistance from this calculation. S is equal to 0.1 G by 0.1 G divided by 99.9. Or we can write shunt resistance as G divided by 999. Okay, so this is the value of shunt resistance in terms of G. Okay, see, if you know that, we can find out the R equivalent now, right? We know we have to find out the total resistance, and the total resistance 1 by R equivalent is going to be 1 by G plus 1 by S. 1 by G plus 1 by S because they are connected in parallel, we know. Yes, so what is 1 by R equivalent? 1 by R equivalent is 1 by G. Okay, nothing to do there. What is S? S is G by 999, right? So then 1 by S is going to be 999 divided by G. See, we have the same denominator. It is going to be what? 1000 by G. That is actually 1 by R equivalent. Therefore, what is the equivalent resistance of the combination? I mean, equivalent resistance of the ammeter now, right? The whole device is equal to G divided by 1000. This much ohm, that is the resistance. So we can say the option B is the correct answer. Understanding the question is very, very important, okay? So you're asked to find out what is the total resistance of the ammeter. You're not asked to find out what is the shunt resistance to be connected. No, you're asked to find out what is the total resistance of the ammeter. Okay, that is G by 1000. Okay, let's move on to the next question. Yeah, it's an assertion reason question. Let us go through the statements. Two long parallel wires freely suspended and connected in series to a battery moves apart. Okay, we'll check. Reason statement. Two wires carrying current in opposite direction repel each other. Yes, repel each other. We can just consider two wires. See, these two wires are suspended freely and we are going to connect them in series. Connect them in series like we are going to connect them in end to end. See, we are going to connect these two ends together with a wire and the other two ends also with a wire with a cell connected, then only current flows through it. So this is a series combination of two conductors. If they are connected in series, right, current will be flowing like in the same, there's only one single branch we have. So if you have a current flowing through the first one, like in this direction, current I, then the current continues in the other one, like, this is the same current I, but it's downwards. So we have two parallel conductors connected in series with a cell. Now we can see from the figure, current flowing through these two are in the opposite direction, right? Two opposite directions, right? What happens when the current flows in the opposite direction? Opposite current actually repel each other, right? We know same current attracts, opposite current repel. See, so this will be repelling apart. What about the statement? They move apart. Yes, they move apart because of the repulsion, they move apart. So your assertion is true. Assertion is a true statement. Fine. Now look at the reason. Reason says two wires carrying current in opposite direction repel each other. Yes, that is the reason for that. So this is also true, and option A, it is like assertion and reason both are correct, and reason is an explanation of assertion, right? Okay, so let's move on to the next question. Yes, a piece of wire bent in the form of a circular loop A carries a current I. The wire is then bent into a circular loop of V of 2 turns and carry the same current. Okay, fine. The ratio of magnetic fields at the center of the loop A to that of B will be. Right. So we have a wire of definite length. We are going to make one loop using that wire. Okay, and we send some current through it. There will be some magnetic field produced at the center. We know the equation, right? Application of Biot-Savart law. We have magnetic field at the center of a circular loop. Okay, later, after measuring that magnetic field, I stretch the wire again, like, I'm going to straight the wire. Now I'm going to make two loops, a loop with 2 turns using the same wire. See, 2 turns. Right. Using the same wire, we are going to make a loop of 2 turns. And we send the same current through it. There will be some other magnetic field produced, right? Because magnetic field at the center of a wire is going to be, loop of wire is going to be 0.I by 2A, mu naught I by 2A. So here current and radius matters. And also if there are n number of turns, that should be multiplied with n also. Okay, yes. So these changes will be there in the second loop. So magnetic field will be different. We have to find the ratio of those two magnetic field. That will be one of the options. Okay, so let us check what will be the magnetic field in the first case. In the first case, remember we have a wire of length L, suppose. If I form a loop of wire using that particular straight wire, that loop may have a radius R, correct? A radius R. See, we need the radius of the loop. It is actually A. We use the letter A, so we can take it as A. A is the radius. We know the total length of the wire will be 2 pi r, which can be equated to L, because that same wire bent to form a circle. So we can say, what is r from this? L by 2 pi. I mean, A. We use it A, right? So we can use the same letter, otherwise it will be confusing. So 2 pi A is equal to L. Therefore, A is equal to L by 2 pi. This is what happens when you bend one to form one loop. So in that case, what will be the magnetic field? Let me take it as B1, right? For the loop A, I'm going to take magnetic field as B1. B1 is equal to mu naught into I divided by 2A is the equation. So 2 into, what is our A actually? L by 2 pi. So we can write it's like L by 2 pi. So 2 gets cancelled. B1 is equal to, that pi goes up, right? Mu naught I into pi divided by L. Okay, this is our first equation. B1 is ready. You're asked to find ratio of that magnetic field with another magnetic field for the new loop. Let us check what will be magnetic field of the new loop again. The new loop, the same wire, we used the same wire of length L. This time we make a loop of 2 turns. So definitely the radius will be something else. Let me take it as A dash. We can say 2 pi A dash, that is the circumference of one of the loops. We have 2 such loops, so 2 into 2 pi A dash can be equated to the length of the wire L. Right? Yes. So what is A dash from this? A dash is going to be L by 4 pi. Yes. Now we write the magnetic field at the center of this loop also. How will you write B2? B2 is going to be equal to mu naught I divided by 2 times the radius A dash, right? Radius A dash. And most important, don't forget to multiply with 2 here. Why? Because we have 2 turns, should be multiplied by the number of turns. So 2 into mu naught I by 2A dash. See, can you just substitute that A dash now? B2 is equal to 2 mu naught I divided by, what is A dash? L by 4 pi. So we have 2 into L by 4 pi. Right? So that pi goes up, these 2 cancel by 2 only. So we get B2 is equal to, this 2 comes up, so we get 4 mu naught I into pi divided by L. This is my second equation. Yes. So we got B1 and B2. B1 is ready here. B2 is ready, see, in equation number 2. You're asked to find out what is the ratio of the two, B1 by B2. See, look at equation 1 and 2. Straight you can say mu naught I pi L. Mu naught I pi L gets cancelled. We get 1 by 4. The ratio is going to be 1 by 4. Yes, so the option D is the correct answer. Magnetic field due to a circular loop at the center. Yes. Next question. 2 charged particles P and Q, each having a charge Q, but of masses m1 and m2, are accelerated through the same potential difference V. Yes, they are talking about the radius of the circular path, right? When we read the question itself, we understood. Yes, they enter a region of magnetic field B, which is perpendicular to velocity, and describes circular paths, as we expected. Yes, of radii A and B, respectively. Then m1 by m2 is equal to, the ratio of their masses is to be calculated. Look at the options. All options are given in terms of A and B, where A and B are the radius of those circular paths. Okay, so we have 2 particles, each of having charge Q. So they have same charge but different mass, m1 and m2. And yet we have to decide which equation to be used, because we have so many equations for R. Radius of the circular path, we have mv by qb, right? So we have R is equal to, this is going to be the momentum and kinetic energy relation, 2me divided by qb, where E is the kinetic energy, and kinetic energy of a charged particle could be 2m q into capital V, where capital V is the accelerating potential, divided by qb. So we have these many equations. So how to decide which equations to be used? See, question is talking about, they say about the potential difference now. See, constant potential difference. So the equation in which we get potential difference is to be selected. Now look at that equation. We have radius R is equal to root of 2mq into capital V divided by q into b. Yes, q into b. Now look at the question once again. It says that particular charges P and Q, the particles P and Q, they have same charge Q. So Q1 and Q2 are going to be the same. So we can take Q as a constant in this equation. Correct? Yes. Now their masses are different. They have same accelerating potential. They accelerated through the same potential difference. V is the same. And they enter the same magnetic field. And 2 is a numerical constant. See? Everything goes. Now, the radius is directly proportional to what? Root of m. That is our conclusion, right? In this particular situation, radius of the circular path is directly proportional to the square root of their masses. So what could be R1 is proportional to root of m1. What is R2 is proportional to root of m2. Correct? Yes. So what could be R1 by R2? See, R1 is given as small a. R2 is given as b. So we can say R1 by R2, which is actually equal to A by B, is root of M1 by M2. Correct? Yes. So look at that. We have M1 by A. So we have to find out M1 by M2 only. So how will you find it out? Square on either side. What is M1 by M2? M1 by M2 will be equal to A by B, the whole square, or A square by B square. We have a matching option. That is option C. Right? Yes, so choosing the equation correctly, that is the first thing, and just understand which are the common terms, take them as constants, form a relation, simplify. Okay, let's move on to the next. A wire of length 4.4 meters is bent round in the shape of a circular loop and carries a current of 1 ampere. The magnetic moment of the loop will be, yes, a question from current carrying loop act as a magnetic dipole, right? We know any current carrying loop can be considered as a magnetic dipole. That means they produce two poles, right? That's the meaning. If the current is flowing in the clockwise direction for you from this side, it produces what? Clockwise current always forms a south pole, right? We know, right? But someone observing from the other side of the loop, that current is anti-clockwise, right? So for anti-clockwise current, there will be a north pole. So one loop itself produces, both poles on either side. That is how we concluded a loop of wire act as a magnetic dipole. Yes. So how will we calculate magnetic dipole of a loop of wire? M is equal to I into A, where I is the current flowing through the loop and A is the area enclosed by the loop. And if there are n number of turns, we can put n also. So here this is only one single loop, so no need of n here, correct? Yes. So length of the wire is given as 4.4 meters. That bent to form a in the form of a circular loop. So we are not given the radius. To find out the area, first of all, we have to find out the radius and then use that area here, pi r square here, it's a circular loop, then multiply with I. N is 1 only, so I is given, current is given as 1 ampere. So just we have to calculate area basically, right? I is 1, N is 1 only. So we will get directly the magnetic moment. So let us find it out. The same logic we used it before. If you have a wire of length L, if you form a loop of wire, like a circular loop of wire of radius R, how can you relate the two? 2 pi r, right? 2 pi r can be equated to the length of the wire. Yes, so radius r is equal to L by 2 pi. Then how will you find out area of the loop? Area of the loop is going to be pi into r square. Substitute the value of r. What is area? Pi into r is going to be L square by 4 pi square. One of the pi gets cancelled. A is going to be like L square by 4 pi. This is what we got. That's the area of the loop. You are given the value of L. L is equal to 4.4. Yes. So we can take that value to the calculation. Now M is equal to, current is going to be 1 into area is pi r square, that is L square by pi. L square by 4 pi. Okay, so L square is going to be 4.4. See, 4.4 into one more 4.4 divided by, that is going to be 4 here, into 3.14 or 22 by 7, whatever it may be, you can just simplify that. Okay, that will give you the magnetic moment, magnetic dipole moment of the loop of wire, which we formed by bending a straight wire into a circular loop. And if you simplify that, you will get 1.54 ampere per meter square. That will be the value. Okay, that was easy, right? Only confusion we had here is like the area is not given directly, that we had to find out. Good. Now, next one. A circular coil of radius 10 centimeter is placed in a magnetic field. Again, magnetic field is given in the vector form. 1 I cap plus 0.5 j cap millitesla. See, I want to remind you something here. This part is very, very important because, that millitesla we may not notice, that conversion, 10 raised to minus 3. So none of your answers may not be matching with the given options. So that is because we forgot to convert this most of the time. Yes. Such that the outward vector normal to the surface of the coil is 0.6 I cap plus 0.8 I cap, j cap. Magnetic flux linked with the coil. We are asked to find out flux linked with a coil. What is the expression for flux linked with a coil? Phi is equal to B into A into cos theta. But this won't work, we know, because we have given these vector forms of B and A. So we have to go for vector B dot vector A. That is a dot product of two vectors. So if you know vectors B and A, we know how to find the dot product of two vectors, right? Yes. So then we have to identify what is B. B is given directly. B is 1 I cap plus the other one is j cap, 0.5 j cap. But remember, it is millitesla, so into 10 raised to minus 3 Tesla. Okay, that conversion I told you. Now, a circular coil. See, your magnetic field is ready for substitution here. That's okay. We have to find out the area now. What is a coil given? It is a circular coil. A circular coil of radius 10 centimeters. Okay, radius is given, you have to find the area then. What will be the area? Area of the loop, see now we'll calculate here only, area of the loop is going to be pi into r square. Radius is given. What is the radius? Radius is 10 centimeter. So we can say pi into 10 raised to minus 2 converted to meters, the whole square. So we get 10 raised to minus 2 times pi, that is meter square. We'll keep that pi there, we'll simplify at the end. Okay, so here we get area of the loop. But this is already in the vector form. We have I cap, j cap, right? It is already in the vector form. To use, to apply dot product later. But area is not in the vector form. We know only the magnitude. How can you convert this into the vector? That is 10 raised to minus 2 times pi, that is a magnitude, into unit vector, right? That is how we convert this into a vector. You are given vector normal to the surface, that outward unit vector, normal to the surface. We know area of any loop is going to be normal to the surface only, correct? If you have a circular loop of wire, area will be perpendicular to the plane of the loop. So that unit vector is given. So we have to just multiply this 10 raised to minus 2 pi, okay? 10 raised to minus 2 pi should be multiplied with what? 0.6 I cap plus 0.8 j cap. Done. This is what we have to do. So we get, see, 0.6 pi into 10 raised to minus 2 I cap plus, opening the bracket, okay, 0.8 j cap into 10 raised to minus 2 pi. So now we have area also in the vector form. Next step is easy. We have to just go for dot product of two vectors. Done, right? So how will you find dot product of two vectors? We have I components and j components. So B dot A. So if you go for B, this is just one I cap. Here I cap is 0.6 pi into 10 raised to minus 2 is a value. So we are multiplying those two. We get 0.6 pi into 10 raised to minus 2. Okay, so I components we multiply together. Now the j component 0.5 and this part 0.5 into plus 0.5 into 0.8 into 10 raised to minus 2 pi. So we can take 10 raised to minus 2 pi common. What do we get? 0.6 pi plus this is going to be 0.4 pi, correct? 0.8 into 0.5 is going to be 0.4. So 0.6 plus 0.4 pi is going to be just, sorry, that pi we have already taken out. So this pi is not there. So we get 0.6 plus 0.4, right? Yes, 0.6 plus 0.4 is going to be 1. So 10 raised to minus 2 pi. Wait, and that is what I told you. There will be a minus 10 raised to minus 3. This is 0.1 into 10 raised to minus 3. Tesla, right? Then 0.5 into 10 raised to minus 3. So altogether there will be 1 10 raised to minus 3 here, and this also there will be a 10 raised to minus 3 because it was millitesla. This part we didn't consider. Yes, into 10 raised to minus 3 Tesla. Sorry, not Tesla, it is Weber, right? Yes, because it is flux. Now we can say phi is equal to, look at this, pi into 10 raised to minus 5. Now check the option, 3.14 into 10 raised to minus 5 should be the answer. And look at the options, all of them are in what? Micro Weber. Micro is the power 10 raised to minus 6, right? So we can just rearrange this 3.14 into 10 raised to minus, sorry, 10 raised to minus 5. That is what the value we got. Now, if you want to make it 10 raised to minus 6, 31.4 into 10 raised to minus 6 Weber. So 31.4 micro Weber should be our answer, which is going to be option C. Okay, so this is how we calculated the flux, dot product and cross product of vectors. Right, we used it both in different calculations. Fine, moving on to the next. Again, an assertion reason question. Assertion question statement says electron and proton enter the same momentum, enter with the same momentum P in a magnetic field B such that P is perpendicular to B. See, P is perpendicular to B means velocity is perpendicular to a magnetic field, right? Direction of momentum and direction of velocity will be the same. Then both describe a circular path. Sure, right? obvious that will be undergoing a circular path only. Yes, so that is a true statement. We know whenever velocity, when v is perpendicular to b, it follows a circular path. No wonder it is correct only. Fine. Reason. The statement says the radius of the circular path described by the charged particle, charge q and mass m, moving in the magnetic field B is given by R is equal to mv by qb. See, that is also a true statement. Right? It is also a true statement. See, radius of the circular path, we know R is equal to mv. Yes, mv by qb. The question says they have same momentum, right? They enter with the same momentum. What is that momentum actually? mv. So R is equal to p by qb. Right? Yes. So they have same momentum. They enter the same magnetic field. Same momentum, same magnetic field. Then the only factor decides the radius is actually charge of electron, one charge of proton, because particles are electron and proton. Their masses are different, but their charge remains the same, right? If they have same momentum, then charge also the same, because proton and electron, they have same magnitude of charge. So we can say R remains the same for both. Radius of proton will be equal to radius of electron. Yes. So that statement is actually a true statement. See, it undergo a circular path of same radius. Assertion is true. And this is the reason for that, right? This is the radius equation. Same momentum means same charge. So radius also will be the same. So we can go for option A. Both assertions and reason statements are true, and reason explains the assertion. Okay. Next one. A 20 centimeter segment of wire carrying 5 ampere current in the positive y direction. Yes. See, be careful about the directions given. Lies along y-axis as shown in the figure. Good. The magnetic field at the point 3 meter, 4 meter, 0 due to this segment part of a circuit. Okay, this segment is. You're asked to find out magnetic field due to a small line element at a given point. Where is that point lying? X, Y, 0. So that point lies in the xy plane. Right? That point lies in the xy plane. Okay, so this is the line element given. It's an application of Biot-Savart law, right? Straight direct application of that. See, we can say magnetic field due to a small line element dB is equal to mu naught by 4 pi I dl sine theta divided by r square. That is the equation. Yes. Now, look at the diagram. See, in this diagram, this is the line element given. See, this is the line element. Its length is given 2 centimeter. So dl value is given. dl is equal to 2 centimeter. Yes. Fine. Current flowing through that is also given. Current is I, which is 5 ampere. Good. Current is 5 ampere. Then mu naught by 4 pi is a constant, we know. I dl sine theta by r square. So dl and I is there. Now we have to find out r and theta. Right? Then only we can find out the distance, r we can substitute, and theta also we have to substitute, because mu naught by 4 pi is a constant. So let us try to understand what is r first of all. Okay, so r, if you want to find out r from the figure, look at this. This point is given like 3 meters and 4 meters. 3 meters along x-axis. So we'll go for 1, 2, and 3. Okay, so this is the 3 meters along x-axis. What is the y-axis value? 4 meters. So if you go up for 4 meters, so let me mark 1, 2, 3, and 4, suppose. Then the point is somewhere here, right? This is the point we are looking for. That point has a magnitude, distance along x-axis is 3 unit, 3 meters, and along y-axis it is 4 meters. If so, r, what is this r stands for? That r is the distance from the line element, from the line element to the point you considered. So this was the point where we have to find out the magnetic field is, So we have to draw a line joining the two. So there will be a distance from the dl to the point P, which we can easily find out now. We have 3 meters on this side, 4 meters on the other. So for sure, this is going to be what? 5 meters, because 4 meters and 3 meters are given. So radius in this calculation, r, is supposed to be 5 meters. See, we found all the values except theta now. Right. So I, dl, r all are ready for substitution. So sine theta we have to find out. Now what is that angle theta stands for? See, in the figure we know angle theta is the angle between axis of the line element. Correct? What is axis of the line element? If you have a line element, the line, straight line passing through the axis is called axis of the line element. So axis of the line element is nothing but y-axis because the line element lies on y-axis. Good. Then line joining the point and the line element, this line, which we measured as r, right? Angle between axis of line element and this line is called theta. That is our theta in the calculation. Yes. So we know what will be the values here, right? Theta, see, this is 3 meters, so this also will be 3 meters. This is we know the hypotenuse is 5, so we can go for sine theta directly. We can find out sine theta directly from the figure. What is sine theta? Sine theta is going to be opposite side by hypotenuse. Opposite is going to be 3, hypotenuse is 5, so we get 3 by 5. All values are ready for substitution. Only one thing you have to remember, 2 centimeters should be converted to meters, 10 raised to minus 2. Now just substitute and simplify. We will get the magnetic field value. So dB is equal to mu naught by 4 pi, correct? Mu naught by 4 pi into I dl sine theta. See, I is going to be 5 ampere, correct? Yes, 5 ampere. dl is 2 into 10 raised to minus 2. Sine theta is going to be 3 by 5. So 3 divided by 5. Sine theta is written already. And r square. What is r? 5 into 5. See, 5 is the distance from the line element to the point. So now you can simplify and find out the value. See, this will be, one of the 5 gets cancelled. See, we have mu 0 by 4 pi. Mu 0 is going to be 4 pi into 10 raised to minus 7. So we have 10 raised to minus 7 here into, see, this is going to be 2 into 3 is going to be 6 divided by 25 into 10 raised to minus 2. Okay, so this is what the magnetic field dB, and you can just simplify that. Okay, there will be one value here, right? This value is going to be the magnetic field. 6 by 25 is going to be 0.24. 0.24 into 10 raised to minus 9. Yes, 0.24 into 10 raised to minus 9. That much Tesla, right? That is our answer. And look at the options. We have 0.24, 2 of them. Yes. So we are confused now which one to be selected. For that, we should know the direction also, because vector form is given. I cap, j cap and k cap given, right? Okay, so now we have to find out the direction also. What is the direction? Direction is going to be like if you have a current flowing along positive y-axis. See, current is flowing in positive y direction. So according to the right hand thumb rule, it is going to be into, correct? It is going, magnetic field at the point B is going to be into. Into is across, like, going in. If this is x and this is y, z is out of it. Look at the diagram. Z is out of the board, right? The third axis. Then the magnetic field is along negative z axis. It is going into. Negative z axis means minus k cap, right? Minus k cap. So we have to go for the option C, because that is the correct answer, minus k cap. Yes. So we got the value as 0.24. Since we had 2 values given, we checked the direction. So minus 1 is the correct one, because it is into opposite of z axis. That means along negative z axis. Okay, fine. Next question. Yes. A circular loop of wire carrying a current T is lying in xy plane with its center coinciding with the origin. Okay. It is subjected to a uniform magnetic field pointing along z axis. The loop will, see, this one we already explained, like, a different form of the question, x and y. See, we have a loop of wire kept in the xy plane with the center coinciding at the origin. Yes. Now it has a current, circular loop has a current passing through it. Then what will happen to this loop? See, this is what we checked before. If you have a current flowing through this wire like I, magnetic field is acting along positive z axis. So magnetic field is a dot, right? It is coming out. In this region, magnetic field is coming out. So we checked the force acting on it, right? We checked the force acting on at different points. You check the question number 1 we did. Yes, so there will be a shrinking force. So force will be acting in all the directions, you know, and because of that, the loop will try to shrink. So will it move along with the force? No. This force and this force, they'll cancel each other, but because of that, there will be a shrinking effect. There is no translational motion because of that. So this loop will not move, but it may shrink. So as per the given options, the most appropriate one is it remains stationary, right? It won't move. Yes. 12th one, a current carrying circular loop of magnetic moment M. Yes, suspended in a vertical plane in an external magnetic field B, such that its plane is normal to B. Yes, so that's one of the most confusing statement in the questions we get. Like, you know, plane is perpendicular to magnetic field. Plane in an external magnetic field such that plane of the loop is normal to the magnetic field. Plane of the loop normal to the magnetic field simply means, you know, magnetic field and area vector are in the same direction, right? Yes, so theta is equal to 0. Good. The work done in rotating this loop by 45 degree about an axis perpendicular to B. Yes. So if you have a plane perpendicular to the magnetic field, we can represent this as the area vector, right? Area vector, fine. And magnetic field in this region is going perpendicular to it, you know, B. And we know, like, you know, what is the magnetic, angle theta here? 0 degree. So theta 1, initial position of the loop, theta 1 is equal to 0 degree. Yes. And theta 2 is given as 45 degree. From 0 degree, it is rotating by 45 degree. So theta 2 is equal to 45 degree. Now, if you know the equation for work done is going to be equal to the potential energy equation, right? Yes, work done is going to be equal to the potential energy is equal to PE, that is, magnetic field moment means MB, right? Into cos theta 1 minus cos theta 2. This is the equation we have. MB cos theta 1 minus cos theta 2. Directly substitute the values. What is M? Magnetic field is M only, right? B is B only, right? So we have M into B. Cos 0 is going to be 1 minus cos theta 2 is 45, which is going to be 1 by root 2, right? Cos 45. Yes, so we can write MB into 1 minus 1 by root 2. And we know the value of 1 by root 2 also, right? Yes, we remember that value 0.707. Yes, or if you take it as 0.7, because you're asked to calculate is closest to 2, so small approximation is fine. So MB, 1 minus 0.7 is going to be 0.3. So 0.3 MB is your answer, option B. Okay, so we have theta 1 and theta 2 values given, just directly substituted. Okay, fine. Moving on to the next. Two thin, long wires separated by a distance A carry a current I. Okay, see, this is I. In opposite directions. Yes, we know parallel conductors we discussed, right, in one of the assertion recent question before. The wires will, yes, see, look at this. Wires are separated and they carry a current in the opposite direction. We know when currents are in the opposite direction, they repel apart, right? There will be a repulsive force. Yes. So you can just go only for repel options. See, either option A or option D. Option B and C are wrong. We already ruled out them because they cannot attract each other. They will be repelling each other. Now, what is a force acting on two parallel wires? F is equal to mu naught I1 I2 divided by 2 pi into R into L. So all the options are like it's given like force per unit length. So if it is force per unit length, it is going to be F by L, which is nothing but mu naught I1 I2 divided by 2 pi R. Yes, the difference here is only I is same in both. Both of them have the same current, I each. So we have mu naught I square divided by 2 pi, and the distance is given A. So 2 pi A. That's supposed to be the answer. Mu naught I square by 2 pi A and repel. So check the first repulsive one, mu naught I square by 2 pi A square. No, mu naught I square by 2 pi A. Yes, so that is the correct answer, option D. Yes, so next one, question number 14. A straight wire is kept horizontally along east-west direction. Okay. If a steady current flows in the wire from east to west, the magnetic field at a point above the wire will point towards. See, mostly whether it is MCQs or like 2-mark questions, this you will be asked to identify the direction. Whenever it is given in east-west combinations in the question, your answer also should be in east, west, south or north. That options only. In that way you have to represent the direction. And here it is easy, we are given the options also in the same way. Yes, so we know whenever we are talking about the directions, you know, the wall in front of us, we can fix it as north. Okay, that is how we solve this. Yes, we fix this wall as north. If this is north, that will be east, this side will be west, correct? So east, north, west, definitely that will be south. Okay, now we have a horizontal wire is kept horizontally in the east-west direction. So east-west direction means if this is your north, see always when you sit in the exam hall or when you sit somewhere in your room, always wherever you sit, in what direction you sit, doesn't matter, fix in front of you, it is north. Accordingly, then east and west. If this is north, east and west. So this is our north for the time being, okay, in front of us, the wall is north. So now take this horizontally, it is from east to west, it's going from east to west, good. If the steady current flows in the direction from east to west, yes, current is also flowing in the same direction, east to west, magnetic field at a point above the wire, yes, if this is your conductor, you know the wire, current is flowing in this direction, this is our north, we already fixed, I told you, east, west, current is flowing from east to west. Now, how will we find direction of magnetic field due to a current carrying straight conductor? Right hand thumb rule, right? So we have to hold this conductor with our right hand, stretching thumb along the direction of the current. Then these 4 fingers gives us the direction of magnetic field. Yes, so current is from east to west. I'm going to hold it in the direction of current, you know, like this. So magnetic field is going around the conductor like this, correct? Is going around. If you have a magnetic field like going around, circular magnetic field line, how will we find direction of magnetic field at any point? It is a tangent, right? It's a tangent. Here it is a tangent. Wherever you go, it will be tangent. Magnetic field will be tangent. Yes. So if you have magnetic field is going around the conductor like this, you're asked to find out direction of field above the wire. So somewhere a point above the wire, when you reach there, your fingers will go tangentially. Tangentially to what direction? Which side was this? It is the north, right? So the magnetic field is going towards north. So the answer will be option C, north. Okay. Yes, easily we solved it. Moving on to the next. Yes, a galvanometer of resistance 100 ohm, question from the galvanometer part, is converted into an ammeter of range 0 to 1 ampere. Okay, so range is going to be 1 ampere, right? The maximum current you can measure using that particular ammeter is 1 ampere. And resistance of 0.1 ohm. The conversion is done by using this resistance, so that is our shunt resistance given, 0.1. Yes, the ammeter will show full-scale deflection for a current is about. Full-scale deflection current is nothing but the galvanometer current Ig, right? That is to be calculated. The current at which the galvanometer gives you a full deflection is called the full deflection current, that is Ig only. Right. So then, how will you find out the magnetic, deflection, full deflection current? So we have Ig into G is equal to I minus Ig into S, right? This was the equation. Whenever we convert it, we connect it parallel. So G and this S, shunt resistance will be parallel to each other. So this is S, we know current Ig is flowing through this. There will be I minus Ig because the total current entering the device is I only. That is a range of a meter, we know, right? This is how it is. So since they are parallel, we equate their potential drops. That's how we derived it. We have to find out Ig from this. So let me take I into S minus Ig into S. Here we have Ig into capital G. Take that Ig terms together. So we have, this is Ig into S, right? When we open the bracket, Ig into S. So when you take them together, Ig is common, which is going to be G plus S is I into S. Now if you simplify this, we can find out Ig. I is given. See, S is given. Even G is also given. All values are given. So let's go for Ig. What is Ig now? I into S divided by G plus S. See, S is going to be, what is S? 0.1. 0.1 into current is 1 ampere, right? The limit is going to be 1 ampere, or the range is going to be 1 ampere. Then divided by G plus S. So into 1 divided by G plus S. G is 100 plus, what is this? 0.1. That is the value of shunt resistance given. So it is going to be 0.1 divided by 100.1, or we can say it is 1 by 1001, or approximator 2, right? It's about, see, look at this. It's about 1 by 1000. 1 by 1000 is nothing but 10 raised to minus 3 ampere, which is 1 milliampere. Yes, so option B is the correct answer. All right. Direct question only, we have to substitute all the values were given in the question also. Now again, a galvanometer question. A galvanometer of resistance for 50 ohm is converted into a voltmeter of range 0 to 2 volt. Yes, range of the voltmeter is given 2 volt. Yes, using a resistor of 1 kilo ohm. That conversion is done by using a resistance of 1 ohm. That is first case. Now, the same galvanometer we are going to convert into another voltmeter whose range is going to be 10 volt. Yes, the resistance required will be, you are asked to find out the resistance to be connected in series with the galvanometer in 2 cases. Right, this is how we convert it. Yes. So we had this equation, V is equal to Ig into G plus Ig into R. How did we find that R value? R we found, V minus Ig into G divided by Ig. This was R, and finally we got R is equal to V by Ig minus G. That was the equation. This is the equation for the resistance, high resistance, to be connected in series with the galvanometer to convert it into the voltmeter. V is the range of the voltmeter, G is galvanometer resistance, Ig is the full deflection current. See, one galvanometer has only one full deflection current, right? If you know the value of Ig, look at the second case. If you just look at the second case only, volt range is given, range is V, that is 10 volt. Galvanometer resistance is also given 50 ohm. If you know just the value of Ig, you can directly calculate the second part. That was the question actually. How much should be the resistance to convert that into this range? The only difficulty in that calculation is like we don't know what is Ig. So if you can calculate Ig from the first case given, that you can use here and you can find out easily what is the value of the resistance. So let us check the first case. In the first case, we will go for R1 is equal to, see, range V1 divided by Ig minus G. See, R and V only will be different in different cases. Same voltmeter, same galvanometer, so Ig and G remains the same. Yes. And these values are given. R1 was 1 kilo ohm. So this is 1000 ohm is equal to, range of that voltmeter was 2 divided by Ig minus, what is G given? 50. So if you take that 50 to the other side, we get 1050 is equal to 2 divided by Ig. Then what is the Ig? Full deflection current. Ig is equal to 2 divided by 1050. Okay, let it be there. We can simplify that later at the end. Now that Ig can be used here, then easily we can find out R2. In the second case, R2 is going to be the new range divided by same Ig and same G, because the same galvanometer we use. Okay. R2 is to be calculated is equal to, V2 is 10 volt. The new range should be 10 volt divided by Ig value we got already. It is 2 divided by 1050 minus G is going to be 50 ohm. See that 1050 comes up, 10 into 1050 divided by 2 minus 50. That's the value of your R0. See, this is going to be 10,500 divided by 2 minus 50. Yes, 10,500 is going to be half of the 10,500. So we get 5,250 divided by, minus 50. So from 5,250, if you subtract 50, what will you get? R2 is equal to 5,200 ohm. That should be your answer. 5,002, everything is given in kilo ohm. So this is going to be 5.2 kilo ohm, right? Yes. So our option is C. Yes. That was an easy one. Moving on to the next. A particle of mass m and charge q is moving with velocity v equals to vxi cap plus vyj cap. If it is subjected to a magnetic field b0i cap, it will move in a, see, straight line path, helical path, circular path, and parabolic path. We know the three different cases we explained. In this case, velocity has x and y component. Velocity is in this direction, but magnetic field just has only x component, right? You know, I cap only. So this is magnetic field direction, and this is the velocity direction. This velocity can be resolved into two components. We know there will be one x component, one y component, correct? Vy and vx. We know what happens now. Because of this, because of Vx, no deviation. Because of Vy, it will undergo circular motion. So as a combined effect, we know that particular charged particle will go in a helical path. That was a case 3 we explained. So the answer is helical path only. Right. 19. A particle of mass m and charge q describe a circular path of radius capital R then in a magnetic field. If the mass and charge were 2m and q by 2 respectively, then what will be the radius, the new radius? Okay, so we know the expression for radius R is equal to, it's given in terms of charge and mass, right? Charge and mass. So we have mv by qb. There is no mention about velocity, so we take velocity as a constant. Mass is doubled and charge is reduced to half. See, this value is taken as R in the first part of the question. It says that value is R. Now what happens to the new radius? What will be R dash? R dash is going to be m becomes 2m, 2 times the mass. Velocity remains the same. Q is going to be q by 2 into b. So we can write this as mv by qb. What are the remaining terms? There was a 2 in the numerator and a 1 by 2 in the denominator. So we get 4 times mv by qb. mv by qb is actually R from equation number 1. So R dash, the new resistance R dash is going to be 4 times R. Correct? 4 times the initial value. So we get option D as the correct answer. Okay, fine. Again, an assertion reason question. Assertion statement. The energy of a charged particle moving in a magnetic field does not change. Yes, energy of a charged particle moving in a magnetic field does not change. We know that because magnetic means the force is going to be F is equal to Q into V cross B, right? Yes. So force is always perpendicular to what? Velocity. Force is always perpendicular to magnetic field also. If force is always perpendicular to the velocity, force will be perpendicular to the displacement also. Because of that, work done by the magnetic force on a charge is always 0. If there is no work done on the charged particle, there is no change in energy also. So the assertion statement, the energy of a charged particle moving in a magnetic field does not change, is a true statement. True statement. Now, it is because the work done by the magnetic force on the charge moving in the magnetic field is 0. That also already we explained. So that is also correct statement. So assertion is true, reason is true, and reason explains the assertion. So option A is the correct answer. Next one. Yes. In a galvanometer shows full deflection for a current of Ig. Yes. So Ig has an actual meaning only. It is a full deflection current. If a shunt of resistance S1, okay, is connected to the galvanometer, it gets converted into an ammeter of range 0 to I. So we are going to convert by connecting a shunt of S1, so range is I. Okay, when the resistance of the shunt is made S2, yes, we are going to connect another shunt resistance, its range becomes 0 to 2I. That means the range is going to be doubled. From I, it changes to 2I. Then the ratio of S1 by S2. See, no numerical values are given, so all options are also in terms of I and Ig. So we can just go for the equation of the shunt resistance. That will give you the final answer. Well, how will you calculate the shunt resistance? S is equal to, we had V by Ig minus G, right? That was the equation for S. Shunt resistance, we got, sorry, we convert into ammeter. Yes, so we know galvanometer is converting into ammeter by connecting a shunt, right? So Ig into G is equal to I minus Ig into S. So what is a shunt resistance? Ig by I minus Ig into S. Sorry, into G. G is the galvanometer resistance. So how can you write shunt resistance 1? S1 is equal to Ig divided by I minus Ig. See, in the first case it was I only, into capital G, equation number 1. And S2 is equal to Ig divided by I minus, sorry, what is the new range in the second case? It is 2I, right? Not I. So 2I minus Ig into G, equation number 2. You're asked to find out what is the ratio of S1 by S2. If you take S1 by S2, we know G gets cancelled, Ig gets cancelled. So S1 by S2 is going to be just the other way around, 2I minus Ig divided by I minus Ig. That is a ratio, and that is the option C. Yes, is the correct answer. Fine. Yes, let's move on to the next question. Two insulated concentric coils, each of radius r, placed at right angles to each other, carry currents I and root 3I respectively. The magnitude of net magnetic field at their common center will be. Yes, so we have two circular loops. One of them is kept like this, and the second one is kept perpendicular to that. The plane is perpendicular to that plane. So this is the way how we keep it. Then magnetic field due to the first one, if you have a current flowing in this one, like, there will be a magnetic field acting in this direction, directed in that way. For the second one, so the second loop, if the current is flowing like this, see, we can go for a magnetic field, then it is, according to right hand thumb rule, it will be like this, B2. Yes, see, direction of the current is not specifically given in the question, that you can decide as you want. Whatever be the direction you take, this will be the result. Like, it can be either B1 like this and B2, or it will be the other way around. Like, whatever be the combination, theta is going to be the same, 90 degree only. Yes, so that is why it is not specifically given. We know what is a magnetic field at the center of a loop. Magnetic field at the center of a loop, B is equal to mu naught I by 2A. A is a radius. Now look at this. We have two identical coils. Radius is R only for both of them. The only difference is I and root 3I. See, current flowing through the circuit, the loops is different. So how will you find B1? B1 is going to be mu naught I by 2A. See, this is the equation we are going to use, right? So then B1 is mu naught I divided by 2R. Equation number 1. Because R is a radius given. Now what will be B2? B2 also is going to be the same, except the current is root 3 times I by 2R, which means B2 is equal to root 3 times mu naught I by 2R. See, equation number 2. See, from 1 and 2, we can say B2 is actually root 3 times B1, right? That is the only difference. Mu naught I by 2R is the same. Only current is different. So B2 is equal to root 3 times B1. You're asked to find out the resultant magnetic field. How will you find the resultant magnetic field of these two, B1 and B2? Parallelogram law of vectors. See, this is going to be like this. Right. So this is the way the resultant magnetic field will be. And we can find out that magnetic field as B is equal to, see, B is the resultant, root of B1 square plus B2 square plus 2 times B1 B2 cos theta, right? This is how we find the resultant of two vectors. Yes, but theta is equal to 90 degree. Yes, so the whole term reduces to 0 because theta is equal to 90 degree and the whole term is 0. Then B is equal to root of B1 square plus B2 square. Here we can substitute this relation, B2 is equal to root 3 times B1. That will be easier. So B is equal to root of B1 square plus root 3 B2. Sorry, root 3 times B1 the whole square, correct? There is no B2 now. B2 is replaced by B1 square. Yes, so then this is going to be B1 square plus 3B1 square, which is actually 4B1 square, 4b1 square root is going to be just 2b1, right? Resultant is going to be 2b1. We know what's the value of b1. b1 is equal to mu naught I by 2r. So b is going to be 2 times mu naught I by 2r. 2 gets cancelled, mu naught I by r. This is the resultant magnetic field at the center of the loop, and mu naught I by r is the option A. This is the correct answer. Okay, so this relation will help you to simplify that parallelogram law calculation easily. Yes. Next one. Yes, a beam of electrons and protons move parallel to each other in the same direction. They attract each other, repel each other. See, we did similar questions before also, but in this case, it is not current carrying conductors. They are just the charged particles. See, electron is moving in a particular direction. Suppose electron is moving in this direction, this electron, and protons are moving in the opposite direction. Is it so? No, they are moving parallel to each other in the same direction. Yes, so proton also should move in this direction. Okay, see, positive charge is moving in this direction, negative charge is also moving in this direction. They constitute current also, right? So there will be a current I1. I1 is the current due to electron flow, which is against the motion of electron. I2 is the current due to the proton flow, which is along the direction of the flow of protons, right? We know positive charge, conventional direction of current. So I1 and I2 are opposite current. We know different current, opposite current actually repel each other. So option B should be correct, right? Next one. A long straight wire of radius A carries a steady current I. The current is uniformly distributed across its area of cross-section. The ratio of magnitude of magnetic field B1 at A by 2, B2 at a distance 2A. So this is a question based on magnetic field due to a current carrying conductor, right? So we have a conductor of radius A, right? Area of cross section. So radius of cross section is A given. Now we have to find out magnetic field at two different points. This is the center of, suppose, the axis of that particular conductor. So we have to consider this is the center of the wire. Then we have to go for a point A and another point B, or a point P here and a point Q, because we are talking about 2 points, B1 at A by 2. So magnetic field at the point B is taken as, at the point P is taken as B1. This distance is going to be half of the radius. Distance from the center is measured, and this distance is going to be 2A. R is equal to 2A, and here R is equal to A by 2. These are the two distances given. So we have to find out magnetic field due to these two and take the ratio. And I hope you remember those equations. Magnetic field outside and inside the wire, correct? Magnetic field outside the wire, mu naught I by for a long straight conductor, mu naught I by 2 pi r. And magnetic field inside the wire is going to be mu naught I by 2 pi a square into r, correct? That we derive it using Ampere's circuital law. So magnetic field inside, that is what the B1 is, right? Yes. Magnetic field inside the wire is going to be, see, inside the wire means if R is equal to A by 2, that point lies inside the wire. So mu naught I by 2 pi a square. Mu naught I by 2 pi a square into R, where R is the distance, A is the radius of cross section. And what will be magnetic field outside? Magnetic field outside the wire is going to be B out, and that will be mu naught I by 2 pi r only, correct? This is how we calculate it. This value we derived by taking a small loop here, a loop of wire, and we can apply the same, we can do the same process. What did we do for a point outside? Then we will get this. Okay, I hope you remember the equation. So now R values you can substitute. R value is A by 2 for B1, it is 2A for B2. So let us calculate B1 and B2. So I'll go for B1. B1 is equal to, what is B1? B1 is the field inside. R is equal to A by 2. So mu naught I into A by 2 divided by 2 pi a square, correct? That's the equation. So A square and A square gets cancelled. one of the A gets cancelled here. See, what is the final expression for B1? Mu naught I divided by 4 pi A, equation number 1. So that is the magnetic field at the point Q, that is B1 as per the question. Now how will you calculate B2? See, B2 is actually from B out. B2 is equal to mu naught I divided by 2 pi into, what is the distance given from the center? R is 2A for the second point, right? So into 2A. So what is your result here? Mu naught I divided by 2 pi into 2 is going to be 4 pi A. So B2 is given by mu naught I by 4 pi A. That is our equation number 2. Yes, so B1 and B2 are ready. Now just compare them. You're asked to find out the ratio of B1 to B2. Okay, so let us take the ratio of B1 and B2. B1 divided by B2 is equal to, what is B1? Mu naught I by 4 pi A. See, B2 is also the same, mu naught I by 4 pi A. So we get the ratio as 1. Yes. Same equations we got, B1 and B2. Yes, so what is the final answer? We have an option A, option 1. Yes, it's B. So ratio is going to be B1 by B2 is going to be 1 only. Right, moving on to the next. Again, an assertion reason statement. Look at this. When radius of a circular loop carrying a steady current is doubled, magnetic moment becomes 4 times. Yes, if you want to check that, what is the expression for magnetic dipole moment? I into A, right? I into A. So magnetic moment is I into A. This is the first case. Magnetic moment, see, 1 second. What is that A stands for? A is the area of the loop. So we can take it as pi r square because we are talking about a circular loop. So area will be pi r square. What is new angular momentum? I into pi into radius is doubled. 2r the whole square, correct? When the radius is doubled. Now we get pi into I into 4r square, which is equal to 4 times I pi r square. Yes, so that statement is true. It becomes 4 times. Yes, the reason state the magnetic moment of a circular loop carrying a steady current is proportional to the area of the loop. That is the reason for that, M is proportional to A. So this is also true and it is a correct explanation of assertion also. Okay. Now, in a moving coil galvanometer, the deflecting torque acting on the coil is related to the current flowing through it as torque acting on the coil. We know torque is equal to mb sine theta, right? This was the equation we have. Torque is equal to m cross b in the vector form. But how will you relate that into current? We can say m is equal to nia, right, into b sine theta. NIA. So what is NIA? Here n is the number of turns, A is the area of the loop, everything is common. So constants. We can say torque is directly proportional to the current. Torque is proportional to I. Okay. 2 thin long parallel wires A and B are separated by a distance R and carrying a current I each in the same direction. The force per unit length exerted by A on B. Yes, so you're asked to find out the force between 2 parallel conductors. See, these kind of questions are repeatedly coming. We have 2 wires, they are separated by a distance R, and next thing we have to check is what are the current. Current is going to be same, I each, so they have current I, and look at the direction also, same direction. A and B, both wires have the current in the same direction, equal current in the same direction. Now, what will be the magnitude of the force that we can calculate? What will be direction of the force? Nature of the force? Attractive, right? Same current. So you can cancel attractive ones like, the repulsive one you can now cancel. This is repulsive. These cannot be the answers. Yes. And then what is the equation for force? F is equal to mu naught into, both of them are the same current, I1, I2 by 2 pi r into L. So you're asked to find out force per unit length, so this part is not there. So we have F is equal to mu naught into I square, because same current, 2 pi into R. And then the nature of the force should be attractive. So mu naught I by 2 pi R. Yes. Okay. See, look at this question. We don't have a matching option. Mu naught I square by 2 pi R. Mu naught I square by 2 pi R you have here, but Yeah, it's correct only, right? Mu naught I square by 2 pi r. Yes, we have a matching option. This one, attractive. Okay, so this one, force will be attractive because current are going in the same, flowing in the same direction. So attractive force, this is the magnitude. So C is the correct answer. Okay, let's move on to the next. An electron enters a magnetic field with speed v. It describes a semicircular path and comes out of the field. The final speed of the electron is. See, you're asked to find out what is the speed of electron after it passes through a magnetic field. It enters the magnetic field with a speed v. So what will be the speed when it leaves the magnetic field? We discussed a concept related to this before. See, work done by the magnetic field, magnetic force on a charge, moving charge, is always zero. If there is no work involved, we know no change in energy. If there is no change in energy, no change in velocity, because kinetic energy remains the same, right? Velocity will be changed because there is a change in direction. Speed remains the same. See, look at the question. You're asked to find out what is the speed of the electron. Speed remains the same because there is no work done. So option B is the correct answer. 29. A current carrying square loop made of wire of length L is placed in a magnetic field. Okay, it experiences a torque which is greater than the torque on a circular loop made of the same wire carrying the same current in the same magnetic field. That we have to check, right? Yes, we cannot decide by reading the statement. They are talking about comparing like torque acting on two loops. One is a square loop, one is a circular loop. And both the square and circular loop are made of one single wire. One wire is bent to form a circle, then later one wire is bent to form a square. Okay, so in which of them will have more torque is the question. And torque, we know the equation for torque is equal to mb sine theta. See, this won't help you to identify the torque magnitude. So we are going to make it like n, only one number of turns. So it is I into A into B into sine theta, right? So we are not going to change any other parameters, like sine theta remains the same magnetic field, same current. Then torque is actually directly proportional to the area associated with the loop, correct? Torque is associated with the area. That is what they say. See, torque on the circular loop made of the same wire carrying the same current in the same magnetic field. Everything remains the same except the shape. Okay, so the one which has greater area will have more torque. Statement says current carrying square loop has greater torque. You know, a square loop made of a wire of length L placed in a magnetic field, it experiences a torque which is greater than the torque on a circular loop. Question says square loop, the torque on a square loop is greater than the torque on a circular loop. This is the statement given. If you want to check it, you have to check what is the area of the square loop and area of the circular loop. Yes, so how will you check the area? We know both of them are made of same wire. One wire of length L is bent to form a square first. If one side, if one square loop is formed, we know one side will be L by 4, right? This will be L by 4. Because one wire of length L is bent into 4 sides. So it will be equally divided. Area of the loop is going to be L square by 16 because L by 2 the whole, sorry, L by 4 the whole square. So this is the area of the square loop. Area of the square loop. We have to check this later. Yes, with circle also. Now, when you go for a circular loop, we have done this before 2 or 3 times already. Radius is going to be R, then 2 pi R is equal to L, correct? How will you find the area? R is equal to L by 2 pi, correct? Area is equal to pi into R square. So area is going to be pi into R is what? L square by 4 pi square. One of the pi gets cancelled. So A is equal to L square by 4 pi. Yes, L square by 4 pi. Here L square by 16 we have. See, L square by 4 pi is going to be L square by 3.14 into 4, correct? 4 into 3.14. So we get 12 point something, 12.56 or something, right? Yes, so that is what we get here, L square by that value, but here it is L square by 16. So area of the circular loop, see, area of the circular loop is actually greater than area of the square. We know torque depends on the area, directly proportional. So torque acting on the circular loop should be more than torque acting on the square loop. But what does the question say? The question say about torque acting on the square is more than the circular loop. So that is a wrong statement, right? That is not correct. Because as per the calculation, circle has more area than the square. So torque on the circle should be more than the square loop. So assertion is a wrong statement. Good. Look at the reason statement. Square loop occupy more area than circular loop. Square occupy more area than circular loop, both made of a wire of the same length. See, even that is also wrong, correct? Because we found the other way around. Yes, so assertion is false and even reason is also false. Right, let's move on to the next. Right, two long parallel wires kept 2 meters apart carry 3 ampere current each in the same direction. Force per unit length on the wire due to the other is, see, force due to the current carrying wires. We know the equation F is equal to mu naught I1 I2 divided by 2 pi r into length. And you're asked to find out the force per unit length. So we can just go for, this is going to be force by length, okay? Mu naught I1 I2 by 2 pi r. All values are given. Mu naught by 2 pi, fine. Let us keep it there. We can simplify that later. I1 and I2, both of them have same current. So that is going to be 9, right? 3 into 3 divided by, what is the distance between the two? They are kept 2 meters apart. So we have 2 meters here, sorry, 2. So all values we substituted already. So 4 pi into 10 raised to minus 9 divided by 4 pi. 4 pi into 10 raised to minus 7 divided by already 4 pi in the denominator also into 3 into 3. So we get 9 into 10 raised to minus 7 Newton. Yes. Yeah, unfortunately, we have two options given. 9 into 10 raised to minus 7. Sorry, only one option is there, right? 10 raised to minus 7. And it says repulsive. Repulsive. Yes. So this question, I think, we check the direction of current. Current are in the same direction. See, I1, I2, both of them are in the same direction. Then the force supposed to be attractive. So it's supposed to be attractive. See, in this paper, the options given was wrong, and 1 mark was awarded to everyone because of this, mistake. It's supposed to be attractive here instead of repulsive. So this is the answer correctly. Okay, right. Next one, assertion reason statement. Once again, the deflection of torque acting, the deflecting torque acting on a current carrying loop is 0 when its plane is perpendicular to the direction of magnetic field. See, we mentioned this before. Plane perpendicular to the magnetic field means, this is the area. Magnetic field is perpendicular to this plane. So this is how the magnetic field is represented. Angle between the two is going to be 0. Theta is equal to 0 degree. We have torque. Torque is equal to mb sine theta. Right? So in this case, theta is equal to 0, angle between magnetic moment and direction of magnetic field. So we have torque is equal to 0 only. So that's a true statement actually, right? When it is kept in this way, theta is equal to 0, sine theta will be 0. So assertion is a true statement. Now reason. The deflecting torque acting on a loop of magnetic moment M in a magnetic field B is given by the dot product of M and B. Now we have the expression torque is equal to M cross B because it is MB sine theta. Dot product is actually MP cos theta, right? Supposed to be. So this is a wrong statement. So assertion is a true statement, but reason is false, right? Yes. Two horizontal thin long parallel wires separated by a distance R carry a current I, each in the opposite direction. The net magnetic field at the point midway between them will be. Yes, this time we have two parallel wires. You are not asked to find out the force. Instead, magnetic field due to these two wires. See, I am going to consider two wires. They carry same current I each in the opposite direction. So let me take current in the first one is going to be in this direction I, but current in the second one should be opposite to that. So this is the current I. Distance between the two is going to be R. See, R is the distance between the two wires. You're asking to find out what is the net magnetic field at a point midway between the two. Midway between the two is somewhere here. So remember, at the point O, distance from the first wire is R by 2. From the second wire is also R by 2, then only it is a midpoint. Yes. So then we have to find out total field here. How many magnetic field can you expect? Each wire will produce, see, this is my conductor number 1 and this is the conductor number 2, suppose. First conductor will produce a magnetic field here, which is going to be across, right? So the yellow conductor produces a magnetic field which is actually across in this region. Whereas the other conductor also produces a magnetic field according to the right hand thumb rule. No, that also is across. So we have two magnetic fields which are in the same direction. So B1 and B2, both of them are cross. So we can say B1 is equal to mu naught I divided by 2 pi into the distance. Mu naught I by 2 pi. The distance is going to be R by 2. So we can take it as R by 2 here. And we get mu naught I divided by pi into R. That is a cross, right? That is B1. And we found B2 also. It will be exactly the same because everything, all the values are same. So B2 also will be mu naught I by pi R, that is also a cross. So if you have two magnetic fields in the same direction, how will you find the resultant? We'll take sum of the two, right? So B1 plus B2. Total magnetic field is B1 plus B2, see? So we get 2 times mu naught I divided by pi R, right? So when you add them, this will be the result. So 2 times mu naught I by pi R. Yes, this question also, check the options. Mu naught I by pi R into, right? Vertically downward. That is the direction. See, both of them are getting into the screen. So we can say this is going to be vertically downward to the screen. So then mu naught I by pi R, we don't have an option here. If it is 2 mu naught I by, it should be pi also should be there. So here also we don't have a matching option. It's supposed to be mu naught I downwards, okay? So these two questions, students were awarded 1 mark each. Okay, this are 2 different sets actually. Okay, so these are the MCQ questions we have, multiple choice questions we have from the last year's different sets of papers. Hope you enjoyed. Stay tuned. We'll be coming up with next video.